let's get started. We've been looking at constraint optimization, and in particular we are looking at what all did we look at? We looked at a equality constraint to start with, then we looked at a inequality constraint, and then we looked at two inequality constraints, and based on that intuition we have built some kind of idea of what or how to solve, not solve, but how to identify whether or not we have reached a useful point in the algorithm. Okay. Then the last thing that we looked at was this kind of a discrepancy between algebra and geometry, right. So we saw, for example, that algebra tells us something which gives us a set of, what did we call them, linearized feasible directions, and depending on how I wrote the specifications. So for example, in here we took the constraint was specified as square of something, and when I took square of something and I tried to calculate the feasible directions, I landed up into trouble. I found out that any direction was feasible, whereas actually that's not the case. So we said that we ended this previous section by saying that we need something extra to bring algebra and geometry into sync, and that something extra is called constraint qualification. Okay, so now let's go a little bit deeper into it. Maybe we can just continue it here itself. Okay. All right. So what is the context over here that we have? It's very simple. Bring algebra and geometry into sync. Okay. In order to do this, now we have spent a lot of time in building up algebra. For example, we had those linearized feasible directions, but so far if you notice, we have not spent any effort in bringing any new tools to understand geometry. We're just sort of going with drawing two-dimensional things. So that's not going to help us when I try to think of a general n-dimensional problem, right. So now is the time that we need to build a few tools to help us firm up geometry. Okay. So in order to do this, I have to define a few new objects which will help us to get to the final geometric object that we are wanting to use. That final geometric object is called a tangent cone. That's going to be the geometric object that I'm going to use to compare it with the algebraic object. The algebraic object was linearized feasible directions. So the geometric object is going to be called the tangent cone. Okay, so let's just mention this so that you know where we are going. Okay, but of course it's not possible to jump into defining a tangent cone in one step, so we have to make a few intermediate steps. So let's have a look at those. So first is what I define as a feasible sequence. Okay, the words are all very common sense kind of words. Feasible. Okay, the words themselves are suggestive. Sequence means a sequence of points. Feasible means something to do with feasibility. Okay, so what the way I define it is, so I take a point x which belongs to the feasible set to start with, and the feasible sequence, remember a sequence I denote with these curly brackets, right. This is a feasible sequence, fs for short. Okay, if two things happen. First is that zk belongs to the feasible set. The second is zk tends to this point x, but there is a small relaxation. We say this for large k. Okay, so this is the idea of a feasible sequence. So what is it saying? To define a feasible sequence, I first need you to tell me what is the point x. Okay, so let's look back at our example that we were discussing yesterday. This is my, right, My same example which we have been using, objective function is x1 plus x2, and I had a constraint c1x which was equality constraint, x1 squared plus x2 squared minus 2 equal to 0, right. So what is the feasible set in this case? Boundary of the circle, okay. So let's take this point over here. Whoops. Okay. Now I want to give you an example of what a feasible sequence is. So remember, I am saying that zk, which is the sequence member, should belong to the feasible set, but for large values of k. So you can assume without any loss of generality that k begins from 1. So let's just note that over here. K is say greater than equal to 1, just a matter of numbering, okay. So for large values of k, all of these zk's begin to live on the feasible set omega and should finally approach this value x, okay. So let's take, supposing I think of points like this. So this is one sequence. So sequence, I start from somewhere wherever else on the top of the circle, and as the sequence index k increases, this zk begins to tend towards my point A, right. So without first defining it, geometrically it makes sense. What is a feasible sequence? It lives on the feasible set and it is approaching the point A as I increase my index, right. Another sequence could be, for example, if I start from, let us say, from somewhere here, and then I start, as I increase my k, this could be another feasible sequence, okay. You can, there are in fact infinite possible sequences that I can define that live on omega and approach my point A, okay. So this was the geometric picture. Let's try to define it, okay. So I'm going to call this as S1. I'm going to call this, give you two examples of a sequence, okay. So S1, so I need to define a x coordinate, I need to define a y coordinate, okay. How would I construct this? The clue is that these points of the sequence must live on the circle. So they should satisfy x1 square plus x2 squared equal to 2, right. So I could define S1 like this. Does that work? Is x1 squared plus x2 squared equal to 2? It works, right. So it's on the circle, and for example, if I take k equal to 1, where do I start from? -1, comma 1. Where is that? So second quadrant, right? Second quadrant. So it's starting from in between over here, and then it's, as I increase k, where is it going? It's following the arrow and falling down into A, right. When k tends to infinity, what does this coordinate become? -√2, comma 0, which is my point A, okay. Similarly, to get S2, there is not much different that I would do. What would I do? Just flip that 1 by k to -1 by k. Some point, right. The feasible sequence can be defined at any point on the feasible set, including the solution point. Okay. So this is a feasible, this is an example of several feasible sequences. Now related to the question you asked, we can also, using the concept of feasible sequences, we can have a different alternate definition of what is a minimizer, or what we are calling a stationary point. So let's call that as point number 2. So local minimizer. So you've got the idea of a feasible sequence. Now using the idea of feasible sequences, if I ask you to come up with a definition of a minimizer to your problem, can you think of a clever way? what would distinguish the minimizer from all other points in the feasible set. And you don't have any calculus to work with, you only have feasible sequences which you can construct at will. What would distinguish the minimizer from any other point in the set? Right, that's exactly right. If I find a point and at that point I find that no matter what feasible sequence I construct, the value of the function at that point is always less than or equal to the feasible sequence. That is another signature of it, right? So no matter in which direction and what way I approach this point, the function value at that point is always less than what is there on the feasible sequence. That is a perfect signature for a feasible point. So you see how we are using geometry to arrive at minimizer now, right? So it's a point at which all feasible sequences, let's move this down a bit, satisfy that f of x is less than or equal to f of zk. Okay, and again we are going to make this statement for large k. Okay, so based on this two simple concepts which we've got a feasible sequence and we've got a local minimizer. Can we conclude that the point A is not a local minimizer? So let's take sequence 1, S1. Okay, so right, everyone knows the figure. So sequence S1 has, let us say, zk. Okay, and let's say sequence S2, let's call the points as wk. Okay, this was our, oops. So this is my zk, this is my wk, this is my point A over here, right? What was to check increasing or decreasing, the objective function I need to take into account is x1 plus x2. x1 plus x2 we already said has what are the contours of constant f? I think, right? So they are like this. So f at zk, let's fill this in, f at x, f zk, f x and f of wk. So the first one, what is the, which way is the inequality? F at x is always greater than, less than or equal to f at zk. It's less than, let's say equal to, and the other one, it's always greater than equal to. So this together implies what? A is not a local minimizer. Yeah, that's quite straightforward, and it's a non-calculus way of arriving at a local minimizer. Remember, this signature will only work for a local minima. Will it give us a global minima also? For convex functions, there is only one minima, so there is no question. But in general, supposing I had my, let's take another example, this is my g of x, which looks like this, right? So supposing I take 2 points A, B, C, and I construct a feasible sequence about point A. It's clear what we are doing? So let's say I start from here or I start from here, and the feasible sequence should tend to A. That's the meaning of a feasible sequence. So this will satisfy the condition that A is a local minimizer. But does it tell me anything about what is happening at B? Tells me absolutely nothing. So that's why this is a signature only for local minimizers. There's absolutely no way that you can get non-local information over here, right? And that's the case with almost, not almost, all the algorithms that we're talking about in this course. They're all local optimization tools, right? You need some other tricks to figure out what's happening in other valleys. Okay. Okay, so we've got feasible sequence, we've got a minimizer. Let's go further. Okay. The third thing that I need to define, having used a the idea of a feasible sequence, is a tangent. Okay. We all know what tangents are. We've been drawing tangents since class 9. Let's formalize this in a way derived from feasible sequences. Okay, so I have our diagram is above over here. Okay, so a tangent is simply I can call it a limiting direction of a feasible sequence. Okay. So keep this diagram in mind over here. This is my zk, this is my a. So as I'm beginning to, supposing so this point x over here, okay. Maybe I need to draw this again. Let's draw this again over here. This is my point x, this is my point zk, this is my point wk. Okay. So what is x minus zk? Which way does it look? I can draw a line from x to zk, right? So this is my x to zk. Similarly, so let's write this. This is x minus zk. Then I can also construct a vector like this. This is x minus wk. Fine. Now, what am I defining the tangent as? A limiting direction of a feasible sequence. Now, imagine what will happen. Supposing I am standing over here. I am standing at the point x, and I am watching the feasible sequence come and collide into me. Can I think of a limiting direction? As the points get closer and closer, so right now you see that x minus zk has an angle like this, but as I start approaching zk coming closer and closer to x, which way do you think this, it will start approaching a tangent, right? As long as I don't exactly become equal to x, I am some small distance away, this limiting direction, that's why it's limiting direction over here, this direction is going to become tangent to the circle. You can see that, right? So that's basically the that's basically how I come up with the definition of a tangent. Okay. So now to mathematically define a tangent, I've got the difference of two vectors zk and x. But there's a problem with that, right? If zk begins to approach x, what happens to the magnitude of this vector? It becomes smaller and smaller. Finally, in the limit, what will happen to the magnitude of this vector? It becomes 0. So how do I rescue it? Divide by the distance, for example, right? So so I need a feasible sequence, and I also need a sequence of scalars which will divide this, right? So that's the common sense way of arriving at it. So in addition to zk which I had, I define some length, so a scalar. Okay, let's call it tk. Okay, which has a property that, what do you think is the most critical property of this tk, which we said is going to be like the length, that as k tends to a very large numbers, what should tk tend towards? 0, right? So it should go as small and at the same rate at what z minus xk is happening, right? That is, I'll just come to that. So tk, let's write that over here. Okay, so give me a minute over there. So the tangent now becomes, I'm going to call it d. So d becomes simply, now I can take the limit nicely. So k tends to infinity, x minus zk divided by tk. Okay. So this as you can see that if tk has this property, then this x minus zk by tk is going to give me a well defined direction, right? It's going to give me, so if I were to draw it, it's going to give me this vector in blue. This is going to be using zk, I get this vector. Now question is, what is a good example or a candidate for tk? So the first idea that comes to our mind is the 2 norm x minus zk. This is good enough for our purposes, okay, but as it turns out in the literature, it's not necessary. Supposing I had defined this as the 1 norm or some other Euclidean, some other p norm of it, it would still work. Why? The only property that it needs to satisfy is this, that for large k, it tends to 0. Okay, so this is actually left to us. So you can choose it in a way that makes the math of the problem as straightforward and convenient as possible. Okay, and this is usually you don't have to stray away from this choice. This works. So as this length shortens and shortens, you can see this gives me a well-defined direction. Okay. So we've got a tangent. If I were to choose wk as my sequence, will I get, what will I get? So x minus wk is kind of pointing bottom right, right? Now as wk begins to approach this way, which way is this vector going to look? Downwards, right? So what is that telling us? It's fine. It's telling us that associated with every feasible sequence, I'm going to come up with a particular tangent direction. There's no reason why we expected everything to give me the same tangent, right? You can see both the blue arrow and the red arrow are legitimate tangent directions to the circle at point A. That's fine.